Hello, everyone. We're going to start off today with solving a simple Coulomb's law problem. Well, somewhat simple. There's a trick to it, and if you use that trick, then it's a trivial problem. If you miss that trick, you can waste a lot of time trying to figure out some algebra. So let's get started on that problem. Turn to my document cam. So here's the problem. We have two essentially point charges. In other words, we're going to pretend these particles are way smaller than the distance between them. They're identical particles, meaning they have the same mass, and they're identically charged. So they both have a charge that I call Q, but we don't know what that Q is. Their mass is 30 grams, and we know that the length of the string that they're hanging from, each one is 35 centimeters, and they're repelling each other, and that's causing the two strings to separate by an angle of about 60 degrees. And our job is to find out what is the actual charge on those charges or on those masses. So what we're going to have to do is take into account many things. One, we have two objects that are actually in static equilibrium. So that brings us up to Newton's second law of motion. Total force is equal to mass times acceleration. But in this case, since they're static, the acceleration is zero. So we get the total force is equal to zero. That's one of the scenarios, or one of the concepts that we'll be using. Another concept we'll be using is that of Coulomb's law. And Coulomb's law says that the force of attraction or repulsion is proportional to the product of the charges, Q squared in this case, and inversely proportional to the distance between them, which I'm going to call D, and you can see I've even labeled right here D over 2 because we're going to have to work out what D is based on L. So we got Coulomb's law, and then we're actually going to have to do vectors. We're going to have to take these forces that are actually acting on it, which includes the tension in the string, the gravitational force, and the Coulomb force, tension, gravitational force. All of those are going to have to combine to give you a force of zero, so that's the vector problem as well. So let's get started on solving it. First off, I know that Newton's second law says the summation of forces is equal to mass times acceleration. But in this case, acceleration is zero. So I get the summation of the forces is equal to zero. And that is a vector equation. So that literally means there's one of these equations for each dimension. In this case, we're just dealing with two dimensions. So there'll be a summation of forces in the x direction equals zero. And there'll be a summation of forces in the y direction equals zero. So that's one of the equations we'll use. That's another equation we'll use. We also know Coulomb's law is in effect. So F Coulomb would be K Q squared in this case over D squared. And that's because I'm choosing to call this distance from here to here D. So that distance is D. Hence, I put the D down here. I'll label that one equation 3. And we're going to go ahead and get started. First off, I'm going to zoom in on this little area right here. Actually, first off, I will determine D. So I'm going to redraw a triangle in such a way that I can find out what D is. The triangle is basically going to be this triangle right here. So my triangle looks like this. It's got L on this side. By symmetry, and what that means is these two things are identical charges and identical masses. So it would be really odd to have this one be, say, 10 degrees and this side be 50 degrees. In fact, the only thing that makes sense is both of them are 30 degrees. And this part right here is D over 2. So I think you can look at this and see that the trig function that relates this side and this side to that angle 30 is opposite the D over 2. So 30 is opposite the D over 2, and this is the hypotenuse. So we'd say sine of 30 degrees is equal to opposite, which is D over 2, over hypotenuse, which is L. So ultimately, I can get another equation for which would be I'll multiply by L and then I'll multiply by 2 on both sides, and I get D is equal to 2L sine of 30 degrees. So that's equation 4. Now that I have that, I can actually use equation 3 because I now know all the parts of it except for the Q, and that's what we're trying to solve for. Now I'm going to zoom in on this particular part so I can work out the equation 1 and equation 2. So what we have here is a point particle, so I'm just going to draw it as a dot. I have a tension acting on it. Now this tension is not acting in the y direction, nor is it acting in the x direction, which I draw here, x and y direction. It's actually acting in between those directions, and it's a tension T. Okay. I know that angle right there again is 30 degrees. Now I also have a force acting on it, the Coulomb force, and the Coulomb force is actually acting in the negative x direction because it's pushing this way, it's repelling, it's being repelled, this particle is being repelled by that particle. So this is F Coulomb. Technically I should have put a vector symbol over my T there. And then additionally there's a weight, mg, pointing downward, and that's again the negative direction, so I'm going to use a red for that. So this is mg, and that's the weight W, if you will. The formula is mg. The symbol would be weight with a vector symbol over it. Now I need to basically take equation 1, the summation forces in the x direction equal to 0. I need to apply that. So in order to do that, I got to find out what the x and y components are of this tension T. So I know that the x component points to the right, the y component points up, so they're both positive directions. So this little vector would be T sub x, and this vector right here would be T sub y. Using trigonometry, I can see that, for instance, this is the tension T on the hypotenuse. So this is the opposite of the 30 degrees. So the sine of 30 degrees is equal to opposite, which is T sub x, over hypotenuse, which is just T. Similarly, the cosine of 30 degrees is equal to T sub y, which is adjacent, of course, over hypotenuse, which is T. So now that I have that, I can work out the x and y components. So the summation force in the x direction, I only have Tx pointing in the positive direction and Fc pointing in the negative direction. And Fc is, of course, this. So I can actually put it in that way. So I'll say Tx is a positive, so Tx minus Fc, but here I'm going to use equation 3. So Fc is going to be K Q squared over D squared is equal to 0. And rearranging, I'm going to say, using Tx is equal to T sine 30, I'm going to say T sine 30 degrees is equal to, so I can get rid of this negative by pulling it on the opposite side of the equals, is equal to K Q squared over D squared. So we're up to equation 3 now. I'm going to call this equation 4 so I can refer to it later. Now using equation 2, that's the summation of the forces in the y direction is equal to 0. In that case, the y direction is only Ty and mg, but Ty, of course, is T times cosine 30. So I'll say T cosine 30 degrees minus mg is equal to 0. And I'll reconfigure it like I did before, pulling this mg over there. I'll get T cosine 30 degrees is equal to mg, and I'll call that equation 5. Okay. So I don't really need the tension. I wasn't asked for the tension. Of course, you might want to know. Maybe you need to know how strong the string must be. You know, for instance, if you're using fishing line, they have something called the tension or the capacity of the string. So or line test, I think that's what they call it. So for instance, you could have 30-pound test string. You want to make sure that your force is not bigger than 30 pounds. So that sort of thing. But in this case, I'm not asked for T, but I am asked for Q, and I know the 30 degrees we can work out. The M I know, the G I know, the K I know, the D I can work out, the sine 30 I can work out. So if I get these two equations related to each other, and I also happen to eliminate the t, I'm even better off. So that's what I'm going to do. And the trick, this is the trick that I told you, if you miss, you might waste a lot of time. This is a case where you want to divide equation 4 by equation 3. I mean, excuse me, by equation 5. So 4 divided by 5 is going to give me t sine 30 degrees over t cosine 30 degrees is equal to k q squared over d squared divided by mg, which of course you can write as k q squared over mg d squared. Okay. Of course, there's a clear simplification here. We can tell, for instance, that the t's are going to cancel out like I suggested, and sine 30 over cosine 30 is just tangent 30. So I'll say tangent 30 degrees is equal to k q squared over mg d squared. This is going to be called equation 6. Okay, I'm just about there. I've got something where I can use for C, but I still have this D problem. But luckily, we already worked out what D is. Equation 4 told us that, I'd already used 4 before. Anyways, we will call that other one 4 prime, since I didn't realize I'd already used it. So this was 4 prime divided by 5. Anyways, that's the number 4. So using equation 4 into 6, we get tangent 30 degrees is equal to k q squared over d is equal to 2l sine 30. So d squared would be 4l squared sine squared 30. So it's mg 4l squared sine squared 30 degrees. Now that's kind of ugly, but once we substitute what our values for tangent and sine are, it gets a lot easier. For instance, we know sine of 30 using our special triangle. So our special triangle right here, 60 degrees, 30 degrees. The 60 degrees is opposite the long side, so that'd be the square root of 3. 30 degrees is opposite the short one, and the hypotenuse is 2. So we can see, for instance, that the sine of 30 is opposite over hypotenuse, that's 1/2. And of course, the tangent of 30 is 1 over square root of 3, which we rationalize to the square root of 3 over 3. So taking this new equation number 7 and substituting those values, I'm going to get the square root of 3 over 3, that's what tangent 30 is equal to k q squared over 4. Now, sine of 30 is 1/2. So sine squared of 30 would be 1/2 squared, which is 1/4. So I'll just put that right there for right now so everybody knows what's going on. And then I have m times g times l squared. Simplifying a little bit, I can clearly get rid of the 4 and the 1/4 because they multiply to give you 1 because they're reciprocals. And I can solve for q, and I get, or actually for q squared, and I get q squared is equal to square root of 3 times m times G times L squared over 3 times K. So finally, I can say Q squared is equal to, the square root of 3 is about 1.73. I'll put it all in the calculator in a second and do it right exactly. That's about 1.73. That's, of course, exactly 3. So I'll put in all these numbers. The square root of 3 times the mass is 0.030 kilograms. Remember, everything has to be in the base unit, so the kilogram has to be used, not the gram. It was 30 grams, so I had to move the decimal 3 places to the left. The G is 9.8 meters per second, and the L was 35 centimeters, but again, you have to use the base unit, so that's 35.35 meters. That's also squared. And I'm going to divide that by 3 times K, and K is about 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. So I should be able to compute Q squared, and I'll do so as follows. I will do square root of 3 times 0.03 times 9.8 times 0.35 times 0.35, and that gives me 0.0638, or excuse me, 0.06238 for the numerator. Now I'm going to divide that. I'm going to divide that by 3 times 9 times 10 to the 9th. And I get 2.31. Actually 2.31, and 1 is an extra digit I'm just carrying, times 10 to the negative 12th. And let's work out the units. That's 2.31, 10 to the negative 12th. Again, I only put in 2 sig figs, so this one's not appropriate to put on there, but since I want to keep all my numbers to the very end and then round, this is a good practice, and I just underline it to remind me that's not supposed to be there. The kilogram meter per second squared, all that is the same thing as a Newton. So kilogram meter per second squared cancels out with a Newton. This 0.35 meters squared gives me meters squared. So that's going to cancel out with that unit. And then all I have is a Coulomb squared in the denominator of the denominator, which means a Coulomb squared. So we in fact get exactly the unit we expect and hope for, which is Coulomb squared. So now I just take the square root of that junk. And in this case, I get 1.52 times 10 to the negative 6. Well, it's 1.52 actually. Times 10 to the negative 6 coulombs. So using proper sig figs, we should get 1.5 times 10 to the negative 6 coulombs, or 1.5 microcoulombs is the charge necessary for that static situation. So there's a lot of different steps of this problem. I'll rehash what we did. We had to use Newton's second law, total force equals mass times acceleration. We had to use Newton's second law, total force equals mass times acceleration right here. But in component form, that's total force in the x direction equals mass times acceleration in the x direction. Total force in the y direction equals mass times acceleration in the y direction. But for a static case, the acceleration is 0, so I got 0 for both of those parts. We also used Coulomb's law, which is kq squared over, in this case, I labeled the distance d, so it's d squared. And we also had to use some basic trigonometry to figure out what d was. It turned out that when you draw this left half of the triangle, you end up getting L as the hypotenuse, D over 2 as the opposite of the 30-degree angle. So D ends up being 2L sine 30. I had forgotten that I used 4, so I ended up labeling this equation 4 later, and that was me being a goober. But we fixed it with putting a little prime mark on it. So we then had equation 1, which is summation of forces in the x direction equals 0. Using these facts about trigonometry in this diagram, I could see that Tx, the x component of t, was in fact t times the sine of 30. So that's what was there, t sine 30 minus kq squared over d squared. Putting the kq squared on this side, then we just get t sine 30, and that became what I know as equation 4 prime. Equation 2, the summation force in the y direction equals 0. That just meant ty minus mg, and of course ty is t cosine 30. So t cosine 30 minus mg equals 0. Again, putting it as t cosine 30 equals mg gives us another equation that I called 5. The trick with this system, solving this system, is to really divide the two. There's other ways you could do it. It just takes a lot of work. Whereas if you're smart enough or experienced enough to catch the ability to divide one equation by the other, you can get rid of the unknown t right off the get-go. The only dangers with this mathematically is if the denominator could in some way be 0. Obviously you never divide by 0, but in this case that wasn't an issue. So when I divided them, I got the t's canceling out and end up getting tangent of 30 degrees equals kq squared over mgd squared. Okay, at that point I started making use of my special triangle, the 30, 60, 90 triangle. Remember, the 60 is opposite the square root of 3, the 30 is opposite the 1, and then the 2 is the hypotenuse. So you can immediately get that tangent of 30 degrees is square root of 3 over 3. The sine of 30 degrees is, of course, opposite of hypotenuse, which is 1/2. So I was able to fill in all that stuff, do all this algebra, and ultimately I got an answer of 1.5 microcoulombs for the charge. I hope that's helpful. Bye-bye.